fixed a couple of mistakes from last time and changed the end after we got to already. So it finishes differently. It's a bit too big for the space, unfortunately. And so just briefly, and so I also put in an assignment, and the idea is that hopefully we can get the important parts of the assignment finished before the end of today. So spend half an hour at least looking at that, just to make sure everything seems to make sense to you and works properly on the computer, and then we can do that tomorrow, and hopefully finish it tomorrow even would be good. But anyway, so this was the first part we talked about, these definitions of abundance, which I think is reasonably clear to everybody. And this we talked about a bit now, which is fine. I think that's all hopefully reasonably clear, but we can discuss it more. And this was the interesting part, where we ran into a couple of problems. So okay, so this is a reaction to form water, but it's also a reaction to destroy water and make OH. There's a double-headed arrow, because technically every reaction can go in either direction. That's kind of a logical necessity. In this case, we're interested in if both reactions are possible, if you have a box containing water and OH, ultimately, how much water do you have and how much OH do you have? Okay, and so the first thing you need to work out is which of these states has more energy, because it comes down to energy because we're talking about thermodynamics, and so that's why we need to work out delta E at the beginning. So delta E, and we can use these bond energies to work that out. To go in this direction, this H2 bond has to be broken, and here, an OH bond has to be formed. That's the only two things that change. The other OH bond is already formed. It doesn't introduce any particular energy. So we have to form an OH bond and break an H2 bond. But I'm going to be a little bit tricky here, actually, because I did put down here that this OH bond technically isn't independent of the shape of the molecule. If you have this situation, or this situation, this hydrogen atom also feels this hydrogen atom. So the energy in this bond makes a difference whether you're in just two atoms stuck together or more, meaning that an H2O to an OH plus H, breaking that bond requires this much energy, whereas breaking an OH bond requires a bit less. So I use that number to be more precise. Anyway, so we can state that this has higher energy, and this has lower energy, because this is a positive number. Like, energy is coming out when you head in this direction. You require energy to go back. And so this is exactly the same situation with rotational energy levels. I mean, you already worked out this ratio in the other assignment, except that now we're going to deal with higher energy state over the lower energy state with exactly the same formula. That's the nice thing about it. Yeah. So this is the same Boltzmann formula, minus E2 minus E1. And now we have an energy to put in there. It makes one assumption, however. Whenever we have an equilibrium, thermodynamic equilibrium, that means that we have an energy, and we assume we just have so many collisions between particles that things like reaction barriers don't matter. I mean, in principle, reaction barrier might prevent a particle reacting. But if you have enough collisions, eventually there'll be a particle with enough energy to overcome that. So we're assuming that there's enough collisions. It's an equilibrium. That's the big step. Okay. Yep. And then the other way we can approach this problem is here I've written this as delta E, the amount of energy that comes out of this system. We can also write it as a temperature. Delta E equals KB. In that case, we get a temperature, if you work out the units, of about, probably, I guess. So this is not an energy, but the temperature is always proportional to the energy. And so what that means is that rather than talk about energy over here, we can talk about a temperature, which just makes it more convenient. Gets rid of the KB, basically. And what it also means is that this is 6,800 Kelvin. So if the temperature here is about 6,800 Kelvin, this will be equal to 1. This will be equal to minus 1 over E. So that means we have about 30% and 60% ratio here. This ratio is about 1 over E. So it kind of gives us an order of magnitude estimate of what temperature will affect this ratio. Because if it's much less than 6,800, this number becomes very large. And we're going to have an exponential which produces very little OH. And if this number is very much smaller than 6,800, this number becomes about 0. This will be about equal. But don't worry about that. We can just put in the numbers and not worry about that. So if we assume, what did I assume? 1,000 Kelvin. Okay, so I'm going to make the assumption that the temperature is about 1,000 Kelvin, which is just an assumption. In this case, this is about what you'd expect in a very hot core. We talked about hot cores as being part of the interstellar cloud family, like where the star is already forming. So this would be kind of appropriate to that situation. That then is equal to 0.001 if you put that in your calculator, or to one decimal place only. So what does this mean? Like we have the equation, we worked out the reaction energy, you put it into this Boltzmann formula, assuming thermodynamic equilibrium, there's enough collisions. And the final conclusion really is that for every OH, another way, for every H2O, other way around. Yeah. Take it back. For every 1,000 H2Os, OHs, you have 1 H2O. Okay, that's the conclusion. The basic idea is that because I've assumed a temperature which is much less than this temperature, which is because of this energy, then we're going to have far more, that's not the right conclusion. I'll do it in words. Okay, so for every OH, there are 1,000 H2Os, meaning nearly all of this reaction is on that side. And that's because of the energy. So this is the equilibrium I was trying to get to. Okay. And so I put that in there as well. Okay, but so, and the point then that came after that was, if you can consider this kind of problem, meaning that there should be a lot more H2O than OH, if you look on this graph, on this list, which is the list of molecules that actually happen in stellar clouds, H2O is down here. And so this is a relative abundance. So for every billion hydrogens, there's one H2O, whereas OH, for every 100 million hydrogens, there's one OH. So what that means is that this is not true. It's the other way. There's a lot more H's than H2Os. And if you put in an even lower temperature, I mean, I chose 1,000 Kelvin here. If you had a lower temperature like a dense interstellar cloud of maybe 10 Kelvin, then this should be even more the other way. There should be even more waters per OH. And this is the point that tells us that in an interstellar cloud, it's not an equilibrium. This assumption of collisions is wrong, which is about where we stop worrying about equilibrium. Because if that's wrong, then there's no point continuing down this particular path of theoretical investigation. And yeah. Okay. So that means we need to then look at things not just as an equilibrium, but how they change with time, because they're in disequilibrium. Their clouds are changing with time. So we need to, first of all, redefine some of these things. You have the abundances. That was already clear, I think. You have a chemical reaction, which I've already described. Except now we worry not just about the final states, but how fast states are occurring. And for that, we need a reaction rate. And we kind of actually already saw this. If you have two hard spheres in a box colliding with one another, one question was how often do they collide? And that led to a collision rate inside a box with particles bouncing off each other. This is the same thing, because a collision is the beginning of a reaction. We know there's a reaction barrier, there's a change in energy, but it always begins with particles colliding. Same kind of idea. Okay. And so to find out how things change in time, we'll just go through the mathematical part first. If you have an equation, A plus B goes to C, that's a reaction, with a rate, which tells us the time, how it changes in time, we then need to write down a differential equation. The idea is that if you have population of A changing in time, that's going to be proportional to this rate, multiplied by how much A and B there is. Because in your box, K is a fundamental parameter. Maybe you remember I said this. K is the rate of how fast two particles would collide if there was only one A and one B in the box. Bouncing around, eventually they'll collide. If there's more than one, there's an entire density of A's and B's, you have to just multiply K by that. The reason it's negative is because this reaction is making the amount of A decrease. It's using up A. So this is a negative number. B is also being used up, so it's a negative number, but it's being used up at the same rate. It's the same reaction. So these are the same two terms. And C is forming, so C is a positive derivative, but it's still the same reaction again. So this is the fundamental idea about how they solve the time dependence of reaction rates, is to write down the equation with a rate, depending on what the reaction is, and then you can write down differential equations. And the solution for a small time step is this kind of thing.
Why are the reaction rates of A and B the same? Like, isn't it possible that what you need from A is less than what you need from B to get some...
Yeah, so we're talking about the case where a reaction, there's many particles in the box, but most of the time they're not colliding with anything. That's kind of an assumption. So an A can collide with a B at any time, but that doesn't affect any other collisions in the box. You never have three particles that collide at the same altogether at once. So it really is proportional. So this rate, this whole term, which is a rate, a derivative, this d by something by dt is a rate. That's the definition of the word rate. So this is a rate coefficient. That's why we have a different name. So really, because these are independent collisions, then 1A or a million B's is the same as 1B or a million A's. Either way, that leads to the same number of reactions happening. Okay, and I put this line in because I felt bad about always writing these equations and not describing them. So is anybody unfamiliar with this kind of calculus? Great. Okay. So the important thing to remember. Oh, yes.
In the most general cases, there are catalysts in the reaction.
Yeah.
So they
So,
Is that catalyst included in?
well, so a catalyst is, once again, that's basically three things coming together at once. Because you've got to have A and B and then the catalyst together. And if you go right back to the beginning, there's this at the end, not particularly accurate, but rough. That was rough calculation that if you have in interstellar conditions, low temperature, low density, then you have a few two-body collisions inside a cubic centimeter. This is not the whole universe. This still takes 14 days, even though there's 10,000 particles in this tiny space. And for a three-body collision, it's more than the age of the universe. So you're right, but it doesn't have an effect in this context. Yeah. All right. Okay. So I came up with an example, basically. We have this reaction. All it is a C and an H2 stick together, making CH2. I won't go through it on the board because I think it's hopefully pretty clear from here, but the idea is that we write down the differential equation, and we're only going to concentrate on C. We're not going to calculate how much H2 is changing, because that's kind of an uncommon thing to worry about in this context. We'll explain why in a second. So the reaction is this rate times this reaction rate coefficient times the densities of H2 and C on the left, and minus because it's going down. And we're going to assume initially that there's a density of H2 of about 10,000 particles per cubic centimeter in an interstellar density. But we're going to assume that this is not going down. In this situation, we have a density of the carbon of only 2 particles per cubic centimeter. So the assumption is that even if all the carbon reacts, we've now gone down from 10,000 H2s to 9,998. So this term really is not changing as the reaction progresses, which is a bit, makes it a bit of an extra assumption, but in this case it's fine. So we have some numbers. We have the reaction rate is 10 to the minus 17 cubic centimeters per second.
Where did you get that info?
Where did I get that number from?
Yeah.
I looked it up. So, right, so, yeah, but where does it come from? Okay, so, well, you can calculate it in principle, although that's very difficult. In this case, it's to do with, we discuss this a bit more later, but it's to do with whether or not the particles are attracted to one another, how physically big they are, and also, some other effects like that.
And what we did when calculating the probability of two particles colliding? Like what we did last class?
Two particles colliding combined with the fact that they've got to get over a reaction barrier.
Oh.
So there's two effects, which we will discuss more in a second. But these are not often calculated because that's actually a very difficult calculation. Generally, they're measured, and they're measured by putting, in principle, carbon and hydrogen in a box for some time, and then seeing how these change with time, and that working out this coefficient by actually measuring dNc by dt directly, or some kind of variation on that principle. It's kind of it's mostly an experimental subject actually. Anyway, so here I've substituted in that number, which I've got from the literature. I've substituted in NH2 because I've assumed it's not changing with time, so it's not a variable, and we have a certain amount of NC, that's the variable we're trying to solve for. And then the solution for this differential equation is of course just an exponential. That's the first order differential equation, which we can, sure somebody, sounds like you already have seen this before. And we have an initial amount of carbon, which I've taken from that value, and you can just draw a graph. The carbon is just going down exponentially. It makes complete sense in the sense that within this box it's reacting, C is disappearing, CH2 is forming. CH2 is forming, it's from the same solution, and we get that kind of behavior, which is pretty common. You see this kind of exponential behavior between reactants becoming products. C is a reactant, CH2 is a product. But most of the time, it's more convenient to draw this on a log plot, which I did here. In fact, it's a log of time and a log of abundance. Not abundance per cubic centimeter, but relative abundance. And I put this in now because this is the convention in astrochemistry to think about relative abundance, where you're considering the amount of carbon relative to the amount of H2. And the reason for that is that you observe something, often you don't know what its density is, even though you did a calculation for density earlier. That's not an accurate calculation, and often it's not possible anyway. So often you don't know what the abundance is, you only know the relative abundance. Because you don't know whether you've got a big box with hydrogen and carbon in it, or a small box with hydrogen and carbon in it. Anyway, so what that means is that this exponential looks like a more interesting kind of curve. We'll see more of those later. Okay. So now, you're asking about how do you know what the reaction rate is? And this is not really a theoretical, rigorous theoretical depiction of it, because it turns out those calculations are really, really difficult. So instead, this is more like the experimental formula people use. And the idea here is that we have the collision rate coefficient. So this is just the probability that two particles will collide. The picture from before the first picture we showed of this problem was two particles, maybe one here and one here, moving. And at some point, they'll collide. Okay? And the idea of this collision was that if you have the two particles moving, this time moving in and out of the board, then there's a kind of shared area this big, where if they're both inside this circle moving in and out of the board, they'll touch, meaning this is where there's just a point of contact. Another particle misses completely. So we're actually interested in this size of these particles, these atoms or whatever, and we want to find how often they'll just touch. And so for that, we actually define not their radius, but a cross-section. That's R, the radius, that's another R. And so it's actually the area of the circle which just contains both particles. This is the cross-section which is relevant to collisions. And I mention that now because it comes up again in a second. So anyway, so there's the probability of particles colliding. That's defined by this rate, defined by their cross-section. So that's this point. Then there's a probability that they have enough energy to go over the reaction barrier. So this is where they collide, and this is where they go over the reaction barrier. And so that energy comes from the energy of how fast they were traveling before they collided. So if you think again to the Boltzmann distribution of moving particles, not the velocity this time, but the energy of the velocity, so the velocity squared times the mass, I guess. Then we get another Boltzmann graph. And so at a certain temperature, if this energy is the energy of the barrier, then all the particles that are traveling faster than that will go over the barrier. This gives us a fraction of all particles within the Boltzmann distribution which have enough energy to say E is greater than EA. So that fraction of the Boltzmann distribution has a formula, which is given by this. Unsurprisingly, it's an e to the minus something formula. And it's not, this is where it's not completely rigorous. This formula is not completely mathematically derivable from first principles in the unique form. But in this case, I mean, people really are measuring these quantities, and they just need a formula that's approximately right, so they can define a Kc, find an EA, and then they'll have a good way of describing what the reaction rate is. For example, if there is no barrier, which happens, I mean, in some cases, a reaction just proceeds like this. No barrier at all, so you really only have the collision rate is what's important. In other cases, you have a collision rate, which depends on the temperature. So what that means is that these two particles are in a box. Eventually they'll meet. The hotter it is, the faster they're traveling, the sooner they'll meet. So actually in the hard spheres in a box problem, two hard spheres moving randomly, bouncing around, eventually they'll collide, and so that the faster they're moving, the sooner that'll happen. So what that means, the collision rate actually has a temperature dependence of power of beta. which in the case of the hard spheres is a positive number. They collide sooner at high temperature, meaning a bigger number here is mean a more rapid collision. That's the idea.
Is there like a name for beta? Like, is it called somehow?
Yeah, this really is a fitting formula. It would be a mistake to add too much physical meaning to that number. Yeah. And if anything, this is useful because this can be written in other ways as well, but this is pretty close to how it's written in that assignment, so I was consistent with that. And this really is the convention. I mean, part of the problem people have is that they don't calculate these rates. They measure them mostly. So if you're making a measurement, you would measure temperature and reaction rate as a function of temperature. And you might, this is a special temperature, 300 Kelvin, because that's more or less the temperature of almost every chemistry laboratory in the world. So there's always a reaction rate measured at 300 Kelvin. And there's sometimes they measure one at 78 Kelvin, which is if that's right, that's the temperature at which nitrogen becomes liquid. So you can measure a rate at that temperature relatively easily, maybe a bit lower. And they might have managed one at 200 Kelvin, and that's it. So then the question is, how do you, and we're in stellar space, we want to know what the rate is at 10 Kelvin. So there's going to have to be some kind of extrapolation going on. And you want it to be physically based, but also you want it to be something you can do easily, because turns out there's a lot of reactions in interstellar space, and so you need to know rates for a lot of them, so you can't spend the rest of your life on every single one working the stuff out. Anyway, so this formula will be useful later. Any questions about that stuff? Have you already finished the first half of the assignment already? Okay, a couple more quick definitions. So most reactions we've looked at are like this. Two things come together, something else comes out. Fair enough. Maybe two things come together, two things come out. Also possible. That's called a two-body reaction because there's two things coming together. Fair enough. It's possible to have a one-body reaction where you have a molecule just all by itself and it breaks apart. Usually not spontaneously, but more likely because something happens to it. That's it. I'll keep that one. And the most common thing to happen is a molecule, CO is a good example, meets a photon. And then you have C plus O. That's basically the picture. I mean, you could think of a photon as being a second body if you wanted to, but that doesn't fit very well within the framework of what we're describing in physics. So it's better to think of this as just an external influence. And then, and you also, of course, have the case of three-body reactions, like I think I've also mentioned. We have three things come together, producing 1, 2, 3, 4, 5, whatever things on the other side. And the reason I put it up is because, I mean, if you ever study this in almost any other context, like maybe you're studying industrial chemistry or you're studying atmospheric chemistry, this is more important than either of these two. This sometimes is more important, but this is usually the most important. But for us, it's completely negligible. And also, just as an example, that if we wanted to write a rate equation for the species C, okay, so I've messed up my units a bit there. In this particular page, NA means NA, like that. Anyway, so if you're interested in the amount of N's of C, that's C here, then in all these reactions, C always appears. So we write a rate equation which considers all possible reactions. That includes the first one, where C is destroyed, one where C is created, so that's a positive term, and two more where C is destroyed, because C is on the left-hand side. It's one of the reactants that's destroyed by the reaction. What we also notice is that this is the normal kind, where you include two densities, density of A plus B. In the case of a three-body reaction, you include all three densities. In the case of a one-body reaction, you're only interested in C. It's all the densities on the left have to be multiplied here. Yeah.
I don't remember why we put a 2, like times 2 in the...
That one?
No, on the first term. Two
No,
times
that's
C.
yeah, that's a mistake. that is a mistake.
And on the first one as well? I remember
Why did I-
the 2 yesterday as well.
There's a 2 in this definition. That's the only 2, I think. That 2. Yeah, those are wrong. But the main point of the slide is to describe this, but mainly I want to show that you can have much longer reaction rates than just one reaction. In fact, this is always the case. It's very rare for a molecule to only be able to react in one way. There's usually 5 to 20 reactions affecting each molecule at any time. Okay, so that was one species, C in that case. So that was basically this reaction, written out again, but not finished. But of all the other species that were involved in those equations, A and B, and also D, there's more they all get an equation because they're all reacting all at the same time. And so what that means is that this we're not going to deal with by hand, but you have a series of equations, one for each species, and each equation includes each species, or at least includes the species that react with others. And in the case of the model you'll be working with in a moment, this includes 500 species, A, B, C, D, everything else, and 5,000 lines. And so it really is just a couple differential equation. So it can be solved in principle. There's a matrix methods, or you can integrate it in time, which we won't do. But the point is that this equation can be written out in full, but then is beyond what a human can analytically solve. But it can be solved numerically. That's just the main idea. So you end up with results like this. So this is showing time in years. So this is actually 10 to the 7, so that's 10 million years. On a log scale, so this is only 10 years. So this last time interval here, say, is 100,000 times longer than this one. And we want to do this because chemical reactions happen on an exponential scale. At the beginning, they're very fast, and then they approach an equilibrium and become very slow. So you need to show it on a log scale. And we also show this on a log scale because it turns out that some species, carbon, nitrogen, oxygen, are very abundant. They exist on a relative scale at about 10 to the minus 4. So one of these has 10,000 hydrogens floating around at the same time. Whereas other species, like CO2, is 6 orders of magnitude less abundant. But still interesting. That's actually still an interesting species. So look at them all at once. This should be a log scale as well. So this is the kind of graph that you look at a lot doing astrochemistry, because this is basically a picture in time of what happens in an interstellar cloud. Yeah.
Those first points are like the real data, like in this moment, or there are just random points?
You mean the beginning over here?
The
Why start here?
initial,
Yeah. Okay.
condition.
So remember that if you have a picture of time going across, I mean, in the beginning, you have basically empty space, where you have maybe one particle per cubic centimeter. A bit later, this space starts to contract under its own gravity, and then you have somewhat denser cloud, a diffuse cloud. More time later, meaning that the number of particles stays the same, but it's condensing all the time. And so what that means at this point, you basically only have atoms. Oops, do that again. Like this, because when it's so diffuse, then there's only atoms present. When it condenses, you start to get some atoms, but also some molecules. It's meant to be an N2 molecule mixing with a nitrogen. And eventually, only when it's fully condensed can you start to form mostly molecules. So this initial conditions of carbon, nitrogen, oxygen is up really high. All these molecules are really low because we're saying we're starting from this situation where it's not dense. Then as it collapses, more molecules can form until eventually you have lots of molecules. You still have more atoms than molecules. In this case, that's not always true, but nonetheless you have orders of magnitude, 10 orders of magnitude more molecules at the end than the beginning. So that's kind of the reason for that. Okay. And so this might be the most important slide actually, for now. So when we have so many reactions, it's not possible to read them all yourself or to draw a really descriptive picture of all of them all at once. So the most important step probably of the field is to do a simplification. Like of all the reactions that are included, what are the ones that actually make the most difference? And then you can show that on a diagram like this really easily. So let's go through that. So one part of the diagram looks like this. H2. So that's that part there. And so what that's trying to tell us is this is the destruction of CH2+, one particular molecule. And it tells us even what the reaction is. It's a reaction from CH2+ going to CH3+. That's what the arrow is telling us. It also tells us that small H2 there, that's actually a reaction with H2. And H2 is kind of a special species because it's 10,000 times more abundant than anything else. Then we don't bother writing H2 in any particular way. It's just always there. There's always a never-ending bath of H2. It doesn't get depleted. And then we have to see that there's 4 H's on this side, H2 and H2, and only 3 on this side. So the full reaction must look like that. So that picture summarizes the full reaction. Okay. There's also some reaction rate, which is not drawn on the diagram, but there is one if you look in the literature. Like this. And so we can also write the differential equation. Reaction rate K1, and it's minus because this reaction is destroying CH2+. And then the 2 densities of the reactants. So that's all kind of encoded in that picture. Okay. The next one is this box and this arrow. We have and this we can write in the same place. This is the okay. So we start with a C+, we form a CH2+. There's an H2 is the other reactant, indicated by that. And this time, everything is accounted for. There's no extra product. So that's fine. And so then we can And so this is important. This arrow is destroying CH2 plus. This arrow is creating it. So there's two effects here. Okay, so the full differential equation for CH2 plus includes two processes because there's two arrows on the diagram. And so that's enough of that. And the other points I just wanted to make about this quickly was there's one more interesting reaction here. The directs another formation route for CH2, CH plus in this case. So what that means is that now we have a reaction where C plus H2, these two things, minus some energy. So this is a reaction with a reaction barrier. And another way we could draw it is like that. And so this is important because that adds one more term to this equation, or not quite. It adds another pathway to form CH2 plus. On the differential equation, we have a C plus H2 following this arrow. In principle, you could follow this arrow as well. The problem is this reaction, of all these reactions, is the only one with a reaction barrier, meaning that if the temperature is below 4,000 Kelvin, like for example 10 Kelvin, then this reaction is impossible. There's never enough particles to get over the reaction barrier. So there's a branching here. This one goes this way, this one goes straight, which depends on the temperature. So if you have 1,000 Kelvin temperature, suddenly this arrow becomes important, otherwise you don't. And the final point I guess to make is that in the reaction network, there's about 100 other reactions involving C plus, CH plus, CH2 plus, and CH3 plus. But compared to these, it turns out they have no effect on the abundance of these species in space. And that's because the reaction rates can be too low. Either they might have a really low value of K, so they're not important, or they might more likely have a really low value of whatever species are involved in those reactions. So this whole network is really not as complicated as it seems because they've included all possible reactions, but they may not all be important. And I think I'll stop there for a while. There's a few more things to talk about, but I think instead it would be good to maybe have a look at this assignment and see if it's making sense at that point, and then we can do some more of this stuff later. So feel free to open that assignment. It's open. Yeah, you can download the files for this assignment. Yeah. So download those and see if the instructions make any sense and get started.